The idea is we have two frames and we want to interpolate between them. So on the left, we see without smile, on the right with smile. And using AI, let's see if we can interpolate the frames in between them to make something that looks like this. And here we go. So there are different algorithms for frame interpolation. One of them is film frame interpolation for large motion. Paper came out by Google. The modification that they did is mostly to the loss function. But before we go into that, let's look at the architecture. So the idea is we get the two frames that we want to interpolate in between and pass them to a unit-like architecture where we encode both of the frames here, concatenate them, upscale them to the output frame, which is the middle intermediary frame. And this is how this was trained on high resolution and also high frame rate videos. And the task was to interpolate between the frames. They have a modified loss function. If you do a simple pixel by pixel mean squared error loss, the loss function is not going to capture interpixel dependencies and it's not going to be suboptimal. But something like a VGG contextual loss, which was initially introduced for style transfer, this works well for keeping the context of a image, and they use something similar to that concept to keep pixel consistencies. So what I'm going to do here is hopefully build a pipeline to interpolate between frames. So let's start with the two frames that we have here. So that's image 1 and image 2. I'm in Jupyter Lab. The code base is on GitHub, implemented for PyTorch. So I'm just gonna import Torch, import, let's say NumPy to manipulate some of the pixels. We're gonna import OpenCV to read videos from disk and write videos to disk. And also from Pillow, I'm gonna import the image so we can resize it if we want later to work with. Path, a bit easier. From Pathlib, I'm gonna import path object. And since we're gonna process many frames, I'm gonna import TQDM to get a nice progress bar. And that's about it. So after we load this, the model we're gonna load with Torch Jet, just in time. I have GPUs available, so I'll set my device to CUDA. The model's weights have been released as float 16, which is pretty lightweight, but only it works with CUDA GPUs. It doesn't work with CPUs. So set my device in precision. Now I can get my model using Torch just in time load, and I need to give it the path to the model that I downloaded. It's just checkpoint. It's called film_net_fp16 version .pytorch. Let's load it, have a look. So the architecture that we saw in the image is basically a kind of semi-unit model. It does some pre-processing here, conv2d. We don't see the details of the convolution layers because it's a Torch jet. It's a Torch script right now, but you get the idea. So now the step would be to set the model in the evaluation mode. I'm gonna rewrite it right now. And 2, I'm gonna pass it to my FP16 precision and also to CUDA device, and I don't want any outputs. Okay, so now we should be ready to go. Let's set my path to current working directory, and I basically have my video and image files in this smile directory, so that's gonna be my path. And I'm ready to basically make inferences with the images that I have. So let's have a look at IMG1. This relatively big image, the man not smiling, and IMG2 is the man smiling. Let's see if we can interpolate between these two frames to find the frame in between, hopefully a man in the middle of smiling. So as a first step, I need to turn my image from Pillow format to Torch format. So let's say Torch from NumPy. And if I pass my image, here I'll get an error because of the typo. Now it expects a NumPy array. So the next step is to turn it into NumPy array. So that's the usual pre-processing of going from Pillow image to a torch tensor. The type should be float 16. So right now it's unsigned integer and the values are between 0 and 255. So I'm going to do a few steps. First is divided by 255. Now it's going to be cast into floats. The D type right now should be float 32, converted using as type to torch, or basically the variable precision that we defined. So the shorthand has changed. Let's say to precision. Now it is float 16. So if this is my first image, Let's call it tensor 1. Basically, my tensor 2 would be the same formula, image 2. Okay. And we also probably have to send it to the device as well, to CUDA. So now everything is on my GPU, both the model and the tensors. So now let's interpolate between the frames. The model's call method accepts 2 frames plus something called image mid. So I'm going to get one of these images, let's say tensor 1, and create a new full tensor of size 1 and 1, and the value here should be 0.5. And this is from the original paper. So we can get, let's say, the image mid, and in the middle, it's going to be a tensor of 0.5 on the same device. So these are the 3 arguments we're going to pass to the model. So we're going to say we are with torch.noGrad, or we can use the new context manager called the torch inference mode. It doesn't matter in this case. Let's get the tensor interpolated, or tensor in the middle. Let's call the model on tensor 1, tensor 2, and img mid. Let's see what the output is. Okay, so we get an error here. The issue right now is if we check the shape of the tensors, tensor 1 shape, we don't have a batch dimension, and it expects the values to be channel first. So 3 should come to the beginning. So let me just permute the shapes a little bit, make sure we're doing everything correctly. So permute, so I want the channel dimension first, so 2, the rest should be the same, 0 and 1, and I'm going to unsqueeze a dimension in the beginning. So let's just copy this for the second tensor, and we should be good to go. Let's see, batch dimension, channels, height, and width. So let's try it again. Okay, so we have our tensor interpolated. It's on GPU, we should move it to CPU. Torch D type is float 16. So let's go from tensor interpolated to CPU. And after we move to CPU, we need to first clamp the value. So if you take the minimum of this and the maximum value, they should be between 0 and 1. Sometimes it is between a negative number and the max would be bigger than 1. In this case, the maximum is. So we probably need to clamp it. So tensor interpolated to CPU. Let's call clamp here. We can use the underscore to do it in place between 0 and 1. Now let's do it again. Now we have minimum greater than 0. Let's see what happened. Clamp. Okay, hopefully it should work now. Yep. So we get the value between 0 and 1. So the next step is to rescale it back to the values between 0 and 255. We also have to modify the shape of the output before we can display it. So right now it has a batch dimension, 3 channels, height and width. So let's take care of that as well. So for now, let's just multiply this by 255. And before we reassign it, let's permute. Let me first squeeze the first dimension. And to squeeze the first dimension, basically take the first index value, which is the batch dimension. So let's call it dnorm. And let's have a look at the shape to make sure everything looks correct. Okay, 3 by height and width. Now we can permute this. So I want the height, then the width, and then the channel. Let's double check the shape. Okay, so it should be fine now. You can have a look at the values. They are between 0 to 55 now. Now we have to cast it into a NumPy format in unsigned integer, 8 bits. So the NumPy value would be just called NumPy here, and you can use as type NumPy's unsigned integer 8 bits. Okay, so now it's ready to be displayed. Let's show it using, we can use either pillow from array to have a look at the intermediate value. Okay, let's put all the 3 frames together and see what happens, the progression of the frames. So let me just create a figure and some axes using matplotlib's PLT subplots. 1 row, 3 columns. So I have 3 axes. The first one, I'm just gonna display one. The second one, I'm gonna display my little NumPy array right here, tensor interpolated, that we just found using the model. And the third one would be my final frame. So these are the 2 frames that we used to get this frame. Let's have a look. Okay, perfect. So yeah, this is no smile, smile with teeth, and it really almost perfectly interpolated between them. Let's make this height and width a bit bigger. So let me pass the fixed size, 6x4, let's say. Let's make it double the size. Okay, here we go. No smile, smile, and it's really high quality. I don't notice any degradations in quality here. Now we can basically turn these two frames that we originally had into a video or a motion. To do this, we need to just interpolate between them. So initially we interpolate between the left and the right to get the middle one. Then we can get the first one, the interpolated one, interpolate between them to get the third one, these two in the middle, so kind of like Newton's method, generate frames in between each and every frame. This would give us more frames, of course, but this can be used in many applications like slowing a video down using kind of super resolution slowdown without losing any quality or causing any flickering. And if we continue doing this enough times, we'll end up with a really smooth motion that will look like this. So to speed things up, let me just combine all the cells that we had here. And let's put it in a function that would basically interpolate between two frames and return the interpolated result. Let me get rid of this, tensor 1 and 2 from the image. Okay, so this is our interpolate function here. Let me just indent it a bit, define an interpolate function that takes img1, img2. That's the only thing we need here. We can pass the precision and device here as keyword argument. Of course, it is by default float, torch float, and device by default would be CUDA. Generate the image mid tensor, turn the image into NumPy array, to torch tensor normalized with a batch dimension, cast it to float 16 on CUDA device with torch no gradients, get the interpolated frame, put it back to CPU, clamp it between 0 and 1. We don't need this part anymore. Denorm it back to 0 and 255. Permute the channel dimension to be the last dimension. So these are the typical steps we take in computer vision. And finally turn it into a NumPy array. NumPy array and cast it back to unsigned integer so we can return this at the end. Okay, let me put the colon here. All right, so the next step is just interpolating between two frames, getting a third frame. Each frame is a NumPy array. Okay, so or I can probably make a pillow image because we are expecting as input the pillow image. So image from array would be a pillow image. So I can write a for loop and say, first let me get my first interpolated image again. So let's say I want 1, 2, 3. So let's say img mid, let's call it that. Img mid is interpolate between img1, the initial image, and the second or final image. And let's see if we output the correct thing here. Okay, so this is what we get, the frame. Now we can append this in a list. So let's say I have a list called my frames and it has img1, img mid, img2. Then I can write a for loop and say frame in frames. So it'll start with img1 and then mid. How about I get the first image and the second image? So let's call it I1 and I2 as the first frame in the frames. So this is so instead of getting the actual frames, let's go through the number of frames. So range length frames. Instead of frame, let's call I index from 0, 1, and 2. So I'm gonna get frames at ith index and I plus 1. Of course, it's not gonna always work because if we are getting the last frame, it's not gonna have I plus 1 frame. So let me just try getting the next frame, except if we don't have anything. Well, for now, let's pass. We can modify this later. So try getting the next frame. Then after you get the next frame, and we don't want to pass here, let's just continue on the loop or break. It doesn't matter, it's the last frame anyways. Then we get the new mid. New mid would be the interpolation between I1 and I2. We have other arguments, everything's fine. And now we want to create a new list of frames, a new one, where we interpolate and add the first frame, add the new interpolated frame, and add the final frame. And we do it for every frame or every pair of frames in our list. So let me create an empty list called new frames. Right now it is empty. After I create the interpolated frame, I want to add the first frame and the new interpolated frame. Then for the next iteration, I'll add the first frame and the new interpolated. And for the final frame, I would add, well, I have to continue because I cannot get the next frame. So I'll just append the final frame. So new frames, let's append I1, image 1. And we want to, this time want to extend because we're adding 2 frames, I1 and new mid. So initially IMG1 and the new interpolated frame would be added. Then IMG mid, new interpolated frame would be added. And then at the end, we want to append IMG2. So if there's no other frame, just add to new frames the final frame. And we should be good to go. So let's run this. We'll end up with a list of frames. Okay, now we have a list of frames. We can either use MoviePy's, so from moviepy.editor, I can basically import video clip, or we can simply use OpenCV to write our frames in the disk. So here's a handy function that will write a list of frames using OpenCV to the disk. It's pretty straightforward. Something we need to keep in mind. Let me just go ahead and write our new frames to the disk. So let's have a look at the new frames. It's gonna be a list of 5 pillow images. So write frames. The first argument is the list of frames, so new frames. The second argument is, do we want it to be slow? Let's keep it at false, or let me set it as true. See what happens. A save index, save it to the disk. I'm gonna put it as, let me change the output directory here to smile as well. So my smile folder, you are recommended to save in AVI. Of course, MP4 should work fine as well. If you're doing it recursively, you might want to do it as AVI uncompressed format so you don't lose quality along the way. Okay, save index, let's set it as, okay, so expect the new frame list to be NumPy arrays. We probably can fix it here. I think it's gonna be much easier. So let's try and fix it. It's OpenCV, so it expects it to be NumPy array. This part is easy to remedy, so new frame list 0 would be width and height. Instead of shape, let's ask for size. And then here we say f equals np array of f. Let's see if this solves the issue. Okay, let's have a look at the output. So we have this output video. Let's see how this looks like. So it's a pretty fast motion. We can repeat this now. We can say now frames are my old new frames. Let's check. We have 5 frames now. So I copied this to my good old frames by using the copy package. So import copy. I want a deep copy. Don't want it to be replaced. So copy, deep copy of new frames would be my old frames, new frames empty. Do it again. Now save index 1. Let's have a second look. Now, since it's taken a bit longer, let me put in TQDM. You should see a progress bar next time. As well, we might wanna resize the image because right now it's pretty large. If high quality is not important in this case, that's really high resolution. Let's check the frames per second here. So we have, essentially we had 5 and now we should have 9, 6, 8, 9. Or if we start with n frames, we'll end up with 2n minus 1 frames. So now we have 9 frames. So let's repeat this maybe several times. And at the end, let me print the length of new frames. So there are many optimization steps that we can take here. One of them is to effectively make a batch out of your images if it fits into your memory. So instead of interpolating 1 frame at a time here, we're going to interpolate a batch of, let's say, 8 or 16 at a time. That should probably speed things up if we don't run out of memory. So we have now 17 frames. So we started with 2 frames. We have now 17 frames. Let me save one of them. And let me see if I can optionally pass the FPS. Yeah, I can pass the frames per second. Let's say 2 frames per second. And slow is true. Let's see how this will look like. So if it's a slow motion with 2 frames per second, of course, it's not going to have really much smoothness and fluidity, but it's going to be good for illustration. So let me write these frames. Output video 2. Now 2 frames per second. Let's see. Okay, so it's kind of, yeah, GIF-like, and it is really long, 16 seconds. Let's make it a bit faster. So let's say 7 frames per second and have a second look. Okay, now it's much smoother. And you can see from 2 frames, we even get the finger motion, which kind of is interesting because in the first PNG image, his hand was behind the laptop and then it is here. So the motion was really smooth. Let's have a second look. It's amazing how AI can guess and estimate everything that we probably can see here. Look, the arm's motion seems relatively